This video is about antidifferentiation by substitution. And basically what it's going to allow us to do is compute antiderivatives that are more difficult, antiderivatives that can't be solved using our most basic rules. Now, these antiderivatives that can be solved using the technique of antidifferentiation by substitution are all basically doing the chain rule in reverse. So this technique is just giving us the chain rule in reverse. So let's say we've got a function like this and we want to take the derivative of it. Well, because I've got a function nested inside another function, if I want to take the derivative, I have to use the chain rule. This is my inside function. And we know we have to use the chain rule because we've got these parentheses and I'm taking this function and I'm raising it to the 100th power. So when I take the derivative, I bring the 100 down and then I multiply by my function to the 1 less power. And that's what the chain rule says to do. It says take the derivative of the outside function, evaluate it at the inside function, and then multiply by the derivative of the inside. The derivative of x cubed plus 4 happens to be 3x squared. When we multiply these two together, we might have a 300 x squared times the quantity x squared plus 4 to the 99th. So that's how we take the derivative. We would use the chain rule. Antidifferentiation by substitution is about doing that backwards. So let's say we started with this. You've got 300x squared times x cubed plus 4 raised to the 99. And you're trying to find the antiderivative. So the question becomes, what function do I take the derivative of to get this? Well, we know the answer. We know that this is the answer right here. But if we didn't know the answer in advance, the question is, how could we know? How could we figure out how to get back to that function? Well, one way that we can do that is this method called antidifferentiation by substitution. Now, if somebody presented me with this integral, the first thing I would ask myself is, do my basic rules apply? Well, I don't have any basic rules for products, so we don't have a product rule. Let's see, I've got polynomial functions. I've got a binomial raised to the 99th. Remember we talked about that technique. If this was squared, I could write it twice in FOIL. I guess I could write that 99 times and distribute, but that would be a lot of distribution. We'd write it 99 times, so we distribute 99 times. And then eventually when we're done, we distribute the 300x squared through. And then we have this very, very long polynomial and we integrate term by term or anti-differentiate term by term. We could do that. But there is a better way. But notice, first of all, that we don't have a rule for this, not in its current form. If I wanted to use a basic rule, that's exactly what I would have to do. I'd have to write this 99 times, distribute, and then distribute 300x squared to everything. So that'd be quite a pain. Now the goal is with antidifferentiation by substitution, the goal is to make a substitution so that when we're done, one of our basic rules will apply. And typically we use the variable u. So you'll often hear this technique referred to as a U substitution. So when I'm trying to do a U substitution to undo this operation for the chain rule, I'm basically letting u be that inside function. So u is typically the function that's nested inside another function. So I'm looking for parentheses. It's a function, it might be a function in parentheses, or a function under a radical, inside an exponential, inside a trig function, something like that. It's a function nested inside another function. And if there's a fraction, and that fraction is not a good candidate for one of our basic rules, then I think, well, maybe the denominator should be my u. But yeah, generally we're looking for parentheses or some kind of grouping symbol to tell us that we've got this function nested inside another function. And so I look at this and I see this might be a good candidate for U substitution, because I've got an inside function right here. This is a potential candidate for u. So I'll write that down. I'll say, let's let u equal x cubed plus 4. And then in order to see if this will work, I need to take the differential of u. So I'm going to compute du. So I first identify my inside function. So it's a function nested inside another function. And then we compute du. And when we compute du, we compare it to the integrand. We see if it's up there. If du is up here as a factor, or a constant times du, we don't care if the constants are off. We can always adjust the constants by multiplying or dividing by just the right thing. Then we can write this entire integral in terms of u, and we'll anti-differentiate with respect to u. So we compute du. We said that's inside this function, so that might be u. Let's compute the derivative, or the differential of u, which is the derivative of u with respect to x, 3x squared times dx. Du is that times dx, and the question is this up here somewhere? Well, sure. That 300x squared could be written as 100 times 3x squared, so we could do that. Now, we could also take this equation and multiply by just the right thing so that I have a 300x squared dx on this side. I think that's what I'll do in this case. I'm comparing this 3x squared dx to what I have up here. Since I have the x squared dx, I know it's going to work, but I don't want a 3 here, I want a 300. So I'll take this equation and I'll multiply both sides by 100, and I have 100 du equals 300x squared dx. And now everything up here can be written entirely in terms of u, because I've got all of this over here. This x cubed plus 4, that could be called u. And 300x squared dx, that's 100 du. All of them can be replaced. So we compute du, we multiplied by a constant to make the substitution just a tad easier. And now we want to write the integral entirely in terms of u. And our hope is, after we do this, that a basic rule will apply. Sometimes you have to do a substitution twice. We call that a double U substitution. We actually use the letter W, right? The integral entirely in terms of U. Okay. All right, so this is what we've got. This is U to the 99th. And 300x squared dx, that together is 100 du. So we've replaced that with 100 du, we replaced that with u to the 99th, and the question becomes, after you write the integral entirely in terms of u, do I have a rule for that? And I go back to my rules and I ask myself, do I have a rule for that? Now don't let yourself be distracted by the fact that that's a u. You integrate u to the 99 with respect to u the same way that you integrate x to the 99. So we do have a rule for that. It's just the power rule. X is just a dummy variable. It's a placeholder that's telling you what your variable of integration is. So we can use a u instead of an x in these formulas. You could use t's, you could use y's, you could use thetas, you can use any variable you want. But that's just a power rule. So I can say, yes, I've written my integral in terms of u. I do have a basic rule for that. Then we anti-differentiate that in terms of u. Okay, so I've got that. I bring my 100 down. Then we bring our u down, add 1 to the exponent, divide by the new exponent. Don't forget to add c. The 100s reduce. So we anti-differentiate. And then we're not quite done yet. Remember, the answer is supposed to be a function that I can take the derivative of to get this. Well, if I take the derivative of this, I get 100u to the 99. There's no x's in it. So we always have to back substitute. U is just a placeholder. It's just a variable we invented so that we could take the antiderivative. You always have to go back to x. We always want to back substitute to that original variable. And our original variable is x. So I want to replace that u with whatever it was in terms of x. In this case, it was x cubed plus 4. So we're replacing u with x cubed plus 4. And then we're adding c. So we back substitute, which just means we're replacing u with whatever it was in terms of x. That was x cubed plus 4 in this example. And if I take the derivative of this, do I get this? Oh, sure, that's the problem we took the derivative of at the very beginning. The derivative of this is 100 times this function to the 99 times the derivative of the inside, which is 3x squared. And we got that, and the derivative of the constant is 0. So if I take the derivative of this piece, I get that. So the antiderivative of this is this. I think this is a beautiful method. It says, if this isn't in the right form, if it doesn't look exactly like the exact way I need it to look so that I can use my basic rules, well, sometimes if this derivative was the result of a chain rule, and we can make a U substitution. So we look for an inside function, we take the derivative. If the x squared dx is up there, and it was, then we can write this in terms of U. If this had an x dx and there's an x squared dx, this method's not going to work. So we need to make sure that this variable part of du is up here somewhere. We can always adjust the constant. We had a 3x squared dx, the constant was 300, so we multiplied by the right constant to adjust the constant so that it matched. And then we replaced everything up here with something in terms of u. That 300x squared dx, that's equal to 100 du, according to our substitution. This is u, so I've got u raised to the 99th. It's that. Then I look at that and I say to myself, do I have a rule for that? I do. So I apply the rule, add 1 to the exponent, divide by the new exponent, and then don't forget to back substitute, because your answer needs to be in terms of the original variable, not this variable that you made up so that you could anti-differentiate it. Okay, so that's the idea. Let's look at some more examples. Students tend to struggle with this because they have trouble identifying u. Sometimes people have trouble with that. Sometimes people can identify u, but they have trouble substituting. They have trouble getting from here to here. So we're going to look at some problems and practice that. And that's going to be the rest of the video. We'll just keep practicing. Okay, so let's practice some U substitutions. So here's a problem. The first thing I ask myself is, do I have a basic rule for that? And I don't, because I've got a product, and there is no antiderivative rules for products. So the next thing I say is, okay, if basic rules don't work, will a U substitution work? Since it's our most advanced tool, it probably will. So what we're looking for here is a function nested inside another function. We want to identify that as our U. You see a function nested inside another function? I hope you said yes. This x cubed is a good choice for you because it's inside the sine function. This is x squared times sine of x cubed. That's not sine times x cubed. You always have to take the sine or cosine or tangent of something. There always has to be an angle there that you're taking, that you're evaluating that trig function at. So this x cubed is inside the sine function, so that makes it a good choice for you. So we identify u. Then if we want to see if this will work, we compute du. The derivative of x cubed is 3x squared, and then we multiply by dx. And then we look at this and we sort of ignore the constant term, and we're focused on that x squared dx. We're focused on the part of this that has a variable in it, the x squared dx part. We say to ourselves, do we have an x squared dx up here? We do. Now, if we don't have exactly 3x squared dx, we can take this equation and we can manipulate it so it looks like exactly what we have up there. I've got a 3x squared dx, and I want an x squared dx. So I'll get rid of this 3 by dividing both sides by 3. So I've got 1/3 times du, and that's equal to x squared dx. And now I can substitute everything. So we computed du, we looked at the du, and we saw that the x squared dx was up there, so it's going to work. And now we want to write this integral entirely in terms of u. So the x squared dx turns out to be 1/3 du, and this is sine of u. Every part here needs to be replaced by something. So I replace the x squared dx with a 1/3 and a du. Normally bring that 1/3 out front, and the du we factor off to the far right, and then that's gone. So the only thing that's left is that sine of x cubed, but x cubed is u, so that's sine of u. So that's my new integral, my integral in terms of u. I ask myself, do I have a rule for sine of u? You bet I do. Look, the antiderivative of sine is negative cosine. This has an x instead of a u, but that doesn't matter. It's just a dummy variable. It's just a placeholder. So we ask ourselves if we have a rule for that, and we do. So then we antidifferentiate with respect to u. So we bring the 1/3 down. We say, what's the antiderivative of sine of u? It's negative cosine of u. So you have a negative and a cosine. Substitute the u back in. Don't forget to add c. And then the last step is to back substitute. Excuse me. So that just means you're going to replace u with whatever it was in terms of x. In our case, u was x cubed. So we're replacing u with x cubed. And that's our answer. You don't have to do this, but when we're practicing, it's good to check, at least for the first few. Remember, you can always check your answer by differentiating the result. So we're taking the derivative with respect to x of negative 1/3 cosine of x cubed plus c. So we bring the negative 1/3 down, and then we take the derivative of cosine of x cubed. That requires the chain rule. X cubed is our inside function. It's not a mistake. The inside function here is always the u when you're doing the antiderivative, so that makes sense. So I've got cosine of u. What's the derivative of cosine of a function? It's negative sine of that function times the derivative of the inside by the chain rule. And then we add the derivative of a constant. The derivative of c is 0. The derivative of x cubed is 3x squared. And let's see if we simplify to get this. I've got a negative times a negative is a positive. 1/3 times 3 is 1. And so I've got an x squared times the sine of x cubed. Is that our original integrand? It is. So that means we did it right. It checks out. The derivative of the antiderivative should always be the original integrand. It should be exactly what we started with. Okay, so let's do another one. All right, I want to identify the inside function. I'm looking for, well, ask myself, do basic rules work first? No, they don't, because I've got a product. So then I look for an inside function. I'm looking for parentheses. So this is probably my u if a u sub is going to work. So we identify u. Then you compute du. The derivative of u is derivative of 4, which is 0, minus derivative of y cubed, which is 3y squared, times dy, that's du. Du is the derivative times dy. And I ignore the 3, and I look for the y squared dy. Do I have that? I do, but I don't have that negative 3. I'd like to get rid of it, so I'll divide both sides by negative 3, which is the same as multiplying by negative 1/3. And then I write my integral entirely in terms of the new variable. Okay. So this part is a u to the 2/3 power. And this y squared times dy, that's negative 1/3 du. So I've got a negative 1/3 over here and a du over there. And then we say, do I have a rule for that? And yes, we do have a rule for that. So we will anti-differentiate. So I bring my constant down. It's the power rule, so I add 1 to the exponent. 2/3 plus 1 is 5/3. And then we divide by the new exponent. Dividing by 5/3 is multiplying by the reciprocal, 3/5. Don't forget to add c. And we get negative 1/5 u to the 5/3 plus c. And then the last thing we need to do is back substitute. That should be in that color. So you replace u with 4 minus y cubed. So I've got negative 1/5 of this quantity, the 5/3 power plus c. That's 4 minus y cubed. And if you want, you could check, you could take the derivative of this. Negative 1/5 times 5/3 is going to be a negative 1/3 out front, times all of this to the 1 less power. So of negative 1/3 times this to the 2/3 times the derivative of the inside. Derivative of the inside is negative 3y squared. The negative 1/3 and the negative 3 will cancel, and we'll just have a y squared times that. So it checks out. If you want, you can write that down and make sure that that checks out. But yeah, you can always take the derivative of this using the chain rule, and that should give you this back. Okay, now this one's a little bit more challenging, but I definitely do not have a basic rule for that. I have cosine of natural log of x divided by 5x. Since I don't have a basic rule for this, we don't have an antiderivative rule for quotients. There's no quotient antiderivative rule. We're going to use the most advanced tool we've got. We're going to assume it's a u sub. So we're looking for a function nested inside another function. I see that that logarithm is inside the cosine function. So that's probably my u. Then I'll compute du. Derivative of natural log of x is 1 over x dx. Now on the surface, you might think there's no 1 over x dx up there. But there is. That x in the denominator is not an x. Since it's in the denominator, if I factored it out, it would be a 1 over x. And that 5 in the denominator, I could factor that out. That should be a 1/5 out front. So I think this time, instead of multiplying by the right constant, I think what I'm going to do is factor out that 1/5 and then write this as cosine of natural log of x times a 1 over x dx. Now, if you're saying that does not look anything like what we started with, you might want to put a placeholder of a 1 here. Multiply straight across. 1 times cosine of natural log of x times 1 is that numerator. And 5 times 1 times x is that denominator. So this works. This is equal to that. And then I see, well, if this is what I'm looking at, this part, that's du. And this is cosine of u. So I end up with the integral, or 1/5 of the integral of cosine of u du. So I chose my inside function, I computed du, and then I was able to write my integral entirely in terms of u. And then our hope is that doing that will allow us to apply a basic rule. Sometimes it doesn't allow us to apply a basic rule and we've got to do something else. Do I have a rule for cosine of u? Yes, I do. The antiderivative of cosine is sine. The antiderivative of cosine of u is sine of u plus c. So we antidifferentiate. And then the last thing we do is we back substitute. That's replacing u with whatever u was in terms of x. In this case, u was natural log of x. And if I take the derivative of this guy now, the derivative of 1/5 sine of natural log of x is 1/5 times the derivative of the outside, that's cosine of natural log of x, times the derivative of the inside, which is 1/x. And if I simplify that 1/5 times cosine of natural log of x times 1/x by writing it as a single fraction, I get my original integrand. So that indicates that we did it correctly. This is actually very similar. You're looking for an inside function. Do you see it? What's the function nested inside another function here? I hope you said it was that 1/x cubed. If you did, you were right. Because that is inside that e to the x function. It's inside that natural exponential function. So I have u equals 1/x cubed. Ooh, I don't know if that's going to work. Is that going to work? Be careful. What's the derivative? Or this can be written as x to the -3. What's the derivative of that? The derivative is -3. So you bring that power down, multiply by x to the 1 less power. Now, a lot of students make a mistake here. Because you've been integrating, some people accidentally add 1 to this power and divide by the new exponent. We're not using the power rule, we're taking a derivative. So that's one of the drawbacks of this technique, is that we have to use derivatives and antiderivatives in the same problem. So you have to be very careful and make sure you're taking a derivative when you're supposed to be taking a derivative, and taking an antiderivative when you're supposed to be taking an antiderivative. So we identify the inside function, it's that, and then I rewrite it this way using my exponent properties so it's easier to take the derivative. Then I compute du, which is the derivative times dx. And then I ask myself, is this up there somewhere? Kind of. That x to the 4th in the denominator, that's the same as that x to the -4th. I don't need the -3 though. So I might rewrite this. This is -3/1 times 1/x to the 4th. That's du. And I've got an 8 here. I guess I could multiply by 1/8 and also divide by -3. I'm not going to worry about that. Instead, I'll just factor the 1/8 out. And this is e to the 1/x cubed inside. And that x to the 4th can be factored out as a 1/x to the 4th dx. and I'll just substitute the 1 over x to the 4th instead. So to get rid of that -3, I'll divide both sides by -3, or alternatively, multiply both sides by -1/3. It's the same thing. So I have -1/3 du is 1 over x to the 4th dx. Okay, so this can be rewritten. That can be replaced by -1/3 du. And then this piece can be written as e raised to the u power, because that was our choice for u. Now this looks like I'm subtracting 1/3. I don't want to do that, so I'll put a little dot there for multiplication. And then don't forget that 1/8 from before. So we've chosen our u, we've computed du, we've adjusted the constant, and then we wrote our integral entirely in terms of u, almost. This is 1/8 times a -1/3 du times e to the u. Okay, so I've got a -1/3 times 1/8 times e to the u du right here. That's -1 over 24 times the antiderivative of e to the u with respect to u. Okay, so let's go through the steps. You choose u, compute du. This is not necessary, but I prefer to do it this way. I adjust the constants, because the goal is just to substitute everything, to replace everything. Now, if I could easily multiply this by a number and get 1 over 8x to the 4th dx, I probably would. But once the arithmetic starts to get sort of complicated in my head and it's not obvious that, and like it's not obvious, and not at all obvious to me that I should multiply both sides by a 1/8 and a -1/3. So I should multiply both sides by a -1 over 24. Like that doesn't occur to me. I don't look at this and say, multiply by -1 over 24 and you'll get the 1/8 x, or 1 over 8 times x to the 4th. I don't think that way. So what I do instead is I get this function by itself. So I get that 1 over x to the 4th dx by itself. And I factor out any constants. And then that constant times that constant gives me that perfect constant to get rid of that constant over there. Anyway, so we adjust the constants as necessary just to make the substitution easier. So I want to replace that with -1/3 du. I replace that with e to the u. The 1/8 I factored out. So we write the integral in terms of u. And then after we write the integral in terms of u, if we've got a basic rule, we antidifferentiate. The antiderivative of e to the u is e to the u plus c. And then the last thing we do is back substitute. So we replace u with a 1 over x cubed. So I have -1 over 24 times e to the 1 over x cubed plus c. Okay, and that's that. Alrighty. Just a few more practice problems. I planned for way too many practice problems, I'm sorry. We'll just do these 3 and then we'll be done. Okay, on this one, looking for an inside function. A good choice for the inside function there is natural log of x. Du is 1 over x dx. This is u cubed du. We've got a rule for that, so we use the power rule. Add 1 to the exponent, divide by the new exponent. Don't forget to add c. And then remember to replace your u with whatever it was when you started. U is natural log of x. Okay, then let's look at this one. There are no parentheses here, but I don't have a basic rule for that. But look, I've got this 1 over x rule. It kind of looks like the 1 over x rule. If there are no parentheses, no grouping symbols, when in doubt, just let u be your denominator. Then du is 3 dx. I don't have a 3, I have a 4. So I think I'll just substitute the dx instead. I'll divide both sides by 3 to get dx by itself. I've got 1/3 du equals dx. Okay, so we bring that 4 out, and we're left with 1 over 3x plus 1, and then dx. This can be replaced by u. Dx can be replaced by 1/3 du. And we're multiplying all those together. So I've got a 4 out front. Dx is replaced by 1/3 du, so I'll factor out the 3, factor out the du. And now I've got a u in the denominator here and a 1 in the numerator. Okay, so this can be rewritten that way. Then I bring my 4/3 down and I antidifferentiate 1 over u. The antiderivative of 1 over u is natural log of the absolute value of u plus c. It's just that rule with the x replaced by a u. And u is replaced by 3x plus 1 when we're done, because you always have to back substitute. I want to save this problem for last, so I want to do some over here. That's almost too simple. We've already done problems like that. U is going to be that. We've done problems like that. U will be that one. Now here's one that we haven't done anything like it before. It has a trig function in it. So I'm looking for a function nested inside another function, and I notice that this is under a radical. So I'm thinking that's probably my u. Now the derivative of tangent of theta is secant squared theta d theta. Now you might think that this is not there, but remember what secant squared is. Secant squared is actually 1 over cosine squared. And there's a 1 over cosine squared d theta right there. So we can rewrite this. This is 1 over the square root of 1 plus tangent of theta. And this 1 over cosine squared of theta d theta, that's over here. And that is the same as du, because derivative of tangent is secant squared, and secant squared is 1 over cosine squared. So this is du. That's a u, and we're taking its square root, and it's in the denominator. So we want to write this entirely in terms of u now. I replace that with a u. I replace that with du. I ask myself, do I have a rule for that? Be careful. It's not natural log of the square root of u. So many students do that. If that exponent is anything other than a 1, you've got to rewrite it and use a power rule. And remember, any radical is actually a rational exponent. So there's an implied 1 there and an implied 2 there. So this is really a u to the 1/2, but it's in the denominator. So when I bring it up to the numerator, that's u to the negative 1/2. Then we add 1 to the exponent, and then divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. Don't forget to add c. And this 1/2 power is the same as the square root. So in order to finish the problem, I replace u with whatever it was in terms of the original variable, which was theta. And that's my answer. So the method is Identify an inside function, compute du. If this is up there somewhere, then you want to write everything entirely in terms of u. And your hope is after you do that, you'll have a basic rule for that. If you have a basic rule, anti-differentiate, and then don't forget to back substitute. Now, this is the last one. On the surface, this looks like U substitution will not work. This is kind of a fancy U sub. This is the exception to the rule. Well, first of all, I notice I've got a product, so basic rules do not apply. So the only possible method I have for solving this is to do a U substitution. So I'm looking for a function inside another function, and I have u equals x minus 5. That's a good choice because it's under a radical. Then I compute du. The derivative of x minus 5 is just 1, so I get du equals 1 dx. And now you might be thinking, it's a dud. It can't be done. I've got a square root of u right here, and du is equal to dx. That's fine. But what about this x? That x over here isn't accounted for in my du. Normally, if that happens, I just quit and I say U sub doesn't work. I have to go and try something else. But this is a fancy U sub. This can actually be done. We can write everything in terms of u. And the reason that we can write everything in terms of u is because I've got this equation involving u to the first and x to the first. So I might be thinking on the surface, it looks like the U sub can't be done because the derivative of u, du, is a 1 dx, and I don't have anything to account for that x. But I can use this equation, the original equation, to write x in terms of u. Because if u equals x minus 5, then x equals u plus 5, and we can just multiply right there. So I've got x is replaced with u plus 5. This is the square root of u, and that's a du. Question is, do you have a rule for that? We don't have a rule for that, but if I write that as a u to the 1/2 power and distribute, yeah, I have a rule for that. So this is a good candidate for U sub, but it doesn't work like all the others. This time, we didn't have anything to account for that x. But since we were still able to write every part of our integrand entirely in terms of u, and then get it to a point so that our basic rules applied, this is a good option. U sub does work. It's just a little bit fancier. My friend and former colleague, Larry Starhill, used to call this a fancy U sub. And I always think of him whenever I do one of these problems. Okay, so Dr. Starhill, or Larry Starhill, would say, let's write it like this. And when we do our fancy U sub, this square root of u can be written as u to the 1/2, and then we just distribute that u. And we use our power rules. You add the exponents there. We get this. Okay, so we were able to choose a u, an inside function, compute du, and then even though it required this extra step, we were able to write everything entirely in terms of u. Once we've written everything entirely in terms of u, we distributed so that we could use our power rule, and now we're ready to anti-differentiate. So we'll have this. We add 1 to the exponent, and we divide by the new exponent. Dividing by 5/2 is the same as multiplying by 2/5. Then we bring the 5 down. Then over here, we've got a u. We add 1 to the exponent. 1/2 plus 1 is 3/2. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Don't forget to add c. And then you multiply straight across. So I've got 2/5 times u to the 5/2 plus 10/3 times u to the 3/2 plus c. It's not our answer yet. We're almost done. You guys know what the last thing we need to do is? Don't forget to back substitute. We need a final answer entirely in terms of u, or not entirely in terms of u, excuse me, entirely in terms of x, the original variable. Right now the answer is in terms of u, and that's not what we want. If I take the derivative of this, I'm going to get a function of u. I'm not going to get that back. If I take the derivative of this and simplify, I know it's shocking. You say to yourself, really? If I take the derivative of that, I get that? Turns out you do. You should check it out. You should try it and see if you get the right thing. Okay, so that's anti-differentiation by substitution. In the next video, we'll do a few examples that involve definite integrals. So we'll do integration by substitution when we've got bounds in those problems.